heads up, fellas. This is one of those journeys where we don't know the destination. So we're going down a lot of different paths here. So we got to turn this mess right here into something a little bit more fancy. Something like this. So in this video, we're going to take a look at the journey that it took to get us from what we just saw to this point right here. And it was definitely one of those A to Z days. So we're going to be looking at some experiments that I did. Took about 5 or 6 iterations before I finally found a design that has really good stable combustion. Something that I think will work. Okay, so this is one of the first series of tests that I did. Now, I make it look easier than it actually is in this video. This burner looks great and all, and it'll do this and that, but to get it to do this is very touchy and finicky. If you don't dial in the air and fuel at precisely the right synchronization, you can have some serious problems. A lot of liquid fuel will shoot out the front and things like that. These are just some different settings that I'm going through. It needs a lot of modification. I can't have fuel shooting out the front of this thing, so we're going to cut this thing in half and put an interior flame wall in there to hold the flame back inside the first part of the chamber and to keep that excess fuel from flying out during fuel change.
All right, fellas, you got to see this. This is a very strange phenomenon, and I wonder if this is actually happening during combustion. I'm going to light this flame. I have a lazy flame on this torch, and I'm using it to observe the flow path of the air. Watch what happens. Now I have this blower turned on, and there's air blowing out of this blower. You can feel it. Watch this. Now I'm not going to do it. You see that? That flame is going all the way to the back. It's burning my nozzle even. That flame is traveling all the way to the back of this combustion chamber. Nuts. Why is it doing that? And it's so crazy. So we've got this backdraft going, which is absolutely phenomenal for combustion stability.
I don't have a glow plug in place, so the lighting procedure for this type of burner is going to be to get the combustion chamber red hot with a blowtorch before we introduce any fuel. Just one little spot, just enough to get us a good puff of vaporized fuel. So I'm just going to hold this torch on the bottom of the combustion chamber, and I'm going to show you this in real time. I know it's kind of boring, but Eric, if you watch this, I want you to kind of see how long it takes to preheat one of these things when you don't have all the extra equipment like the high pressure pump and stuff needed for an atomizer nozzle. Besides that, atomizer nozzles at this low of a power output don't really exist. I'd have to make it. You can get them for, 55,000 BTUs and all that, or maybe even higher. So I'm just getting this thing hot here, and I'm going to add fuel as soon as I see some red hot temperature there. You see we're just now starting to get some vaporization. There's a lot of air bubbles in the fuel line. This is the first time that I've ignited this burner since we've changed it. Now you see that weld bead? It's about almost halfway across the combustion chamber. There's actually a firewall in there. It's about a 1/2 inch tall, an annular firewall. It's going to hold some flame and that excess fuel from flying out the front end, so I don't have a fire on the floor every time I go to light this thing. That was definitely something I noticed in the first couple of tests, that during fuel adjustment, you'll get all this excess fuel, and it's not getting burnt. Well, it's got to go somewhere, and there we go, we're lit. Definitely pretty cool looking burner, that's for sure. I probably didn't need to preheat it that long, guys. What just happened right there is the air bubbles in the fuel line, I assure you that. Every time you prime one of these for the first time, the air bubbles in the system make it a pain in the neck. So now that we've got them all purged out, we can fire this thing up, and impressed with, once it gets going, it's pretty nice. It does have some vaporization problems, and this would be a high soot burner if you run it in certain settings. In a setting like this, we could run it and not have any soot problems, but this is low power output. This is probably only about 10 to 20,000 watts of power we're looking at right here. If that, I'm probably way overestimating, because this is not a high velocity flame with an air compressor. This is just a blower. I believe we're using about 150 watts of power right here. We go up to 300 watts max. That's the maximum sacrificial power that I observed during this test. Now, I understand that grating that I have in the front of this is never going to last, but I wanted to test it out because I have a manufacturer who makes silicon carbide products for me. So in theory, I could make that front grill out of silicon carbide if we decide that the turbulence characteristics are desirable. So that's just kind of what I'm looking at. I don't expect that piece of metal to last. We're just kind of using this as a test bed. If it does something I like, then I'll go ahead and draw up the dimensions and send them over to Frank and have it turned into silicon carbide. And that would last without burning up on us. Probably about a year of non-stop operation. 365 days, 24 hours a day. So far so good as far as combustion stability goes. As I said, getting the fuel to atomize at a burner this small, the equipment doesn't exist for it. The pumps pump too much fuel. The problems are never ending. So this fuel is not being atomized by traditional spray nozzles. I'll show you guys what the spray nozzle on this one looks like. It's 24. There's 30. $60. Man, that is bright. That thing is bright. It's going to have a lot of soot production though.
Okay, so we had a drastic increase in performance there with those changes. I don't think I have any footage of that interior wall. One thing I am going to do is remove this IR screen that was just made to give us some infrared radiation.
All right, fellas. This time, now that the fuel line is primed, it should fire up right away. So let's see how much easier it is. I'm just going to heat this chamber up again to give us kind of a primary vaporization that we need to get the process started. Then subsequent to that, the fireball itself becomes the fuel atomizer. So there's no clogging or high pressure gear pumps needed, none of that stuff. And this allows us to turn it up and down because, as I said, with typical high pressure atomizer nozzles, if you turn that gear pump down, the fuel doesn't atomize anymore. An atomizer nozzle typically only works in a very narrow band of flow rate. So not too cool when you want to adjust the flame. So you see there, it lit up a lot easier now that it was primed. I probably could have tried a little bit sooner before I turned the fuel on. You could tell when I turned the fuel on because you get that big puff of smoke coming out of there. So this is without the stainless steel corrugated or perforated sheet that I had stuck in there. This is just straight open. There is a very intense fireball that travels all the way down the center column of the cyclone and surrounds the nozzle in a fireball. And we kind of seen that with the blowtorch experiment we did in the beginning of the video. And after doing these experiments, I now understand why tornadoes shoot hail out of the top. These vortexes cause a vacuum, and that vacuum is going to travel to the area of lowest pressure. So if you have a tornado flying around in the sky, the lowest pressure is way high up in the atmosphere and the highest pressure is down low. So that vortex is probably pumping huge amounts of air from the ground up into the atmosphere. Because like I said, when I put my hand up against this nozzle, I can feel a central vortex vacuum, you guys. So it is pulling a fireball from the front of the flame all the way to the rear of the combustion chamber. And that is causing this tremendous combustion stability. You see here, even though the fuel pump is pulsating, this is the fuel pump doing this. The fuel pump at low settings doesn't pump very consistently. So that's more of the fuel pump, not the combustion chamber itself that's doing that. I did some experiments that kind of shows how these fuel pumps do that on lower settings. But nonetheless, even with this fluctuation in fuel, we have tremendously stable combustion because of the vacuum in that central vortex is pulling that flame from the front of the flame front into the rear. So this thing is, if we had a decent fuel pump that wasn't giving us that fluttering, we'd be okay. It seems like everyone I try does this. So far, so good. Here, let's edit out of some of this and see what this thing can do. All right, so I'm going to crank up the air a lot higher here and get us a blue flame going. I got to do some more testing on this setting to see how long this can be sustained. As you can see, we are still getting some fuel sputter there. Inside of a firebox, the heat of the firebox will help stop that from happening. If you put this inside of a firebox, that little bit of splatter will completely combust. But even still, the silk production of these types of burners kind of concerns me on a cold heat exchange. I may abort the mission here and just build a mobile air compressor system for this project. We're going to run this thing on 10 gallons of diesel and see what it looks like after 10 gallons. And if it's fouled out and really dirty, I'm not so sure what I want to do here, because I've built burners that can run for years without ever even clean. So why would I subject this project to this here? And like I said, the atomizer nozzles are set to run at a certain setting, and that's it. So we wouldn't have as good of a temperature control as we need. And in this case, we don't want to melt the plastic on top of the soil in the vineyard where this boiler is going to be engaged in organic weed control. So kind of a bad situation. All right, so this point here, I think I cranked the air up even higher, and we do seem to get possibly 100% combustion there. Still hard to tell. I'm just worried about getting diesel fumes and stuff all over the vines and all that. I mean, there it looks like we're close to 100% combustion, but that's another one of my concerns. Even with these Beckett burners and those other types of burners like that, they don't burn as good as a high velocity burner can. They just can't do it. So I don't know. We may go with the high velocity burners just for the simple fact I know that they have the most complete combustion available, and we wouldn't have to worry about contaminating the vineyard with diesel fumes and all that nonsense. Like I said, all this spatter you see would totally combust inside a firebox. I have videos on waste oil burners that do that, that shows how inside the firebox that's not an issue. Here I decided to try a quick little experiment and slide a silicon carbide nozzle over the top, and something kind of strange happens. That central vacuum vortex that we had is gone now. There's a choke that takes place that causes that vortex to happen later on down the stream, and I think as a result it just causes some bad combustion characteristics. It doesn't like that at all. I added some more fuel right there to see if that mitigates the problem, but now you can see we're no longer getting hot enough to vaporize that fuel. I didn't turn the air up any higher than this. I probably could have turned it up a lot higher and did some testing in that range, but here pretty quick a bunch of fuel basically just starts dumping out of this thing because it's not vaporizing it. You can tell there's a fireball in the back of this thing. Look how it's looking like a flashlight with a straight beam of light coming out of it. That's that fireball that's in the back. Okay, so here's a clip of me seeing what the sacrificial power is and what the fuel setting's at. Now, what I might do tomorrow is take some fire brick and shroud that flame in fire brick, because I believe if we got that fire brick nice and hot, we would definitely burn the rest of that little bit of spray of fuel. I might even try another stainless steel shroud right there. I'm going to turn the fuel, I think I turned it all the way up here. Yeah, we're at 100 right there on the fuel. I don't have the flow rate on this yet, guys. My objective was to just get this damn thing working and then start figuring out how much fuel it burns. So, some well-placed ceramic or refractory or some silicon carbide would definitely benefit the exterior of this thing, kind of help burn that secondary stuff. That fireball is going all the way to the back, and that velocity is not the true velocity of that flame. The camera is creating an illusion based on the frame rate. It actually looks like it's every bit of 2,000 to 3,000 RPMs, like barely perceptible. Every once in a while you can tell that it's spinning though. So that's where we're at. We're going to try some fire brick wrapped around that flame next. Oh, there it is. A fireball was going all the way to that back wall there. See how the nozzle is completely covered in soot? That's what would happen to a preheat coil on the inside of it. And also, this soot buildup is what's going to happen to the walls of our boiler with this type of burner. So this burner has some disadvantages. It's going to put off a very sooty flame. It's okay for heating air, like in a heat exchange or something, but when you're going to heat the cold walls of a boiler wall, what I'm getting at is you'll have to clean the boiler walls on occasion, and I'd rather that not have to be the case, but we'll see what happens. We'll see what happens.